Welcome to all in this next lecture, that is the continuation of relations. So now here in this lecture we will study about the composition of relations. So suppose A, B and C, here we have the three sets, and R is a relation from A to B and S is a relation from B to C. Then the composition of R and S denoted by ROS, this is the R composition S, is a relation from A to C. Here we have the two relations R, that is on the set A to B, and S is the relation set B to C. So now when we find the R composition S, so that will be the relation from R A to C, and it is defined as ordered pair in R composition S are A C elements, where AB belongs to R and BC belongs to S, and there exists B belongs to B, capital B set. So now let's take an example. How can we solve the composition and how can we find the composition between R and S? So here in this example we have the set A, elements are 1 2 3 4. B set has the elements A B C D, and C is the elements X Y Z. So and relation R is given the ordered pairs 1A 2D 3A 3B 3D, and in the relation S we have the ordered pair elements are Bx Bz By Dz. So now you have to compute here R composition as ROS, right? So how can we compute this? So we can calculate this is R composition S. So you see here, this is our R set, this is our S set. So now first come to the first ordered pair of R, that is 1A. 1A, so 1 is related to A, but here you see that A is not related to here. A is not related to any element in S, right? So now we have to leave this. Now come to the second element ordered pair, that is 2 to D. So now 2 is related to D. Now see here, D is related to which element? So we see that D is related to Z here. So 2 is related to D and D is related to Z. So now our 2 is related to Z. So that is in our R composition S to ordered pair to Z. So like that you have to check that R composition S, like similar like a transitivity property. To transitive property you check that in one set only, and here you have the two relations. So between these you have to check the composition, means like the transitivity property, right? So now come to the point 3 to 3 is related to A. So now when 3 is related to A and we see that here A is not related to any other element, so now we leave here, leave this. So now we come to the next ordered pair, that is 3 related to B. So now we see that 3 related to B here in the this relation. So now see here, B is related to X, 3 is related to B and B is related to X, it means that 3 is related to X here. Now again you see that 3 is related to B and B is 3 is related to B and B is again related to Z also. So we have to consider this also. So now our 3 is related to Z. Now come to the next, that is 3 is related to D and we see that here D is related to Z. So it means that 3 is related to Z, and already this ordered pair elements are in our relation R composition S. So now our R composition S elements ordered pairs are these 2Z, 3X, 3Z. It's clear how to compute composite composition. Okay, so this is the one way to compute the composition. Now the another way is by the using arrow diagram. How can we represent the composition? And here you, I think you can clearly know that how can we calculate R composition S. So here we have the same, the last example, R relation is this and S relation is this. So now here we make here the, this is are the A set elements 1 2 3 4, B set elements A B C D, because we say that our R relation is the R relation is the from the between the set A and B, and S relation is defined B cross C. So we said here the B elements A B C D and C elements are X Y Z, right? So now and here after this we compute our R composition S. So R composition S, by the definition, which sets are there? A and C. So A elements are 1 2 3 4 and C elements are XYZ. So now see that how can we compute R composition S. First we see that here according to relation R, 1 is related to A, right? So now check here. A is here in C's S set. A is related to anyone? No. A is not related to any one element of the XYZ. So we have to leave this. Now second, 2 is related to D. So 2 is related to D. Now check that D is related to which element here? D is related to Z. D is related to Z. It means that our in our composition as 2 is related to Z. You can see here 2 is related to Z. Next, we come to the 3 is related to A. 3 is related to A. But we see that in S relation, A is not related to any element, right? So we can leave this. Now come to the next. 3 is related to B. So now 3 is related to B, and we see here B is related to X. So now our 3 is related to X in our composition S. Next, come to the uh, 3 is related to B. 3 is related to B, and B here B is again related to Z also. So now 3 is related to our Z. Next here we see that 3 is related to D. So 3 is related to D and D is related to Z. So already we have that 3 is related to Z. So like that, by the arrow diagram we can compute this, that what are the elements in our composition is 2 is related to Z. So 2Z, 3 is related to X, so 3X, and 3 is related to Z, so 3Z. So these are the elements. So earlier in earlier method we see that our answer is this, our R composition S is this, and here is same, means this is the second method. You can calculate the R composition S by the using diagram. Okay, so now this is the another way. One another way is also we can find the R composition S, that is the matrix method. So we already know about the matrix method, earlier we studied about this. So here we have the same example, R relation is this and S relation is this given. So now first we make the matrices of this relation R and this relation S. So our MR matrix for the relation R and MS matrix for the relation S, right? So now what is so first we have to form the matrix relation, matrix MR. So how can we form MR? So in earlier lecture we studied that if we have the relation, so we from the relations ordered pair elements we can form the matrix. So now we see that R is a relation of the set A and B, A cross B, and A elements are 1, 2, 3, 4. So these A set we take the elements here in the rows, and B set elements we take in the columns. So a B set was A, B, C, D, right? So now we take the elements of the matrix here. Here our ordered pair is 1A. 1A means we have the 1 here in this position. Which ordered pairs are in relation R? So at that position we have the 1 in the matrix. Otherwise other elements are 0. Right? Remember this thing? So now next element of the pair is 2D. So our 1 is now at the 2D position. So now next ordered pair is 3a, so our next one is in 3a, and 3b, so next element is in 3b, right? Next is 3d, so another one is for 3d, right? So we write here our all relations ordered pair elements, right? So remaining part elements are the 0, right? So this is our the MR matrix. Now similarly we can form the MS matrix, and S is the relation between B and S. So B elements are A, B, C, D, and C elements we have the X, Y, Z. So now the first ordered pair is BX. So BX means one is there in BX position. BZ, so next one is in bz position. Cy element is there, so next one is cy position, and next element is in dz position, so other elements are here 0. So this is our the matrix MS, right? So now if we have the matrix MR and MS, so how can we calculate the R composition S? So we can calculate by the matrix R composition S, MR composition S. This is equivalent to MR multiplication MS. If we multiply in both the matrices, then we can find the R composition S matrix, right? So now for we here multiply. So in earlier lecture we see that how can we multiply this. So now we multiply these two matrices. So after multiplication, what will we get? Here we have the 1 2 3 4 elements, and the our rows columns are x y z. When we multiply this, because this is the order is 4 by 4, this is the order is 4 by 3, so multiplication is possible because the last 4 by 4 last element and the first element are same, and remaining as 4 3. It means that our multiplicated matrix is 4 by 3, right? Means 4 rows and 3 columns are there. So now when we multiply these matrices, then we will get, first when we multiply this element to element and addition, then we will get 0 0 0. Next we get 0 0 1, 1 0 2, and 0 0. So when we multiply this MR and MS, then we get this matrix. So now this is the R composition S. So now the what is our composition S here? The non-zero entries here in this matrix, which are the non-zero matrix. So this is called the R composition S position. So now the elements are here. R composition is here. First is the non-zero element. What is that position? 2z. So our first ordered pair is 2z here. Second is the another known as zero entries here 1, and that position is 3x. So our next ordered pair is 3x here. Next here we have the non-zero entries is 2. So it means that the what is the position of this 2? This position is 3z. So this is our the 3z ordered pair elements are there. So now this is the our R composition S. So by this matrix method we can calculate our R composition S, and we see here we can see that our relation, our answer is same like the earlier methods. So answer will be same, only the difference in the methods, right? So here you see, you can see that here if we get the 2, because we did the multiplication, right? So any number, any non-zero number will be comes to the here, only you have to check that at which position we have the non-zero entries. So that position is your the ordered pair elements of the R composition S. Clear? Okay, so now let's come to the next point, that is the powers of relations. So using the composite way of combining relations, similar to function composition, allows us to recursively define power of a relation R on a set A. So now what is the definition? Let R be a relation on A set, then the powers R to the power n, where n is R 1 2 3, right, up to, so are defined recursively by, if we suppose we need to calculate R, right? So R1 is our relation, right? So now here we need to calculate r to the power n plus 1. So if we have the set only a set is there, right? So now, and we need to calculate r2, r3, r4, r to the power 2, r to the power 3. So like that, r to the power n plus 1 you can calculate is like that, r to the power n composition r. Means if we suppose you need to calculate r2, r to the power 2 r square, so r square means r composition r, right? If you need to calculate r to the power 3, so it means that first you need to calculate r composition r, then you need to calculate r square composition r, then you will get like that the n to the power r to the power n plus 1. You can calculate this. Clear? So now let's take an example for this. Here we have an relation r is given, the elements 1 1 2 1 3 2 4 3. So now here what we do here we calculate r square. So what will be the r square? R square means r composition r. So r, this is r, the r relation, we have to find the composition with r also. So r composition r. So similarly, how can we find the composition? When we find the composition, then we will get this. How can we get this? First we see here the 1 1, right? So 1 1, now check here, 1 is related to which element? 1 is related to 1 here. So in our r square, r composition r, we have the 1 is related to 1. Next, 2 is related to 1 here. And here we see that 2 is related to 1. So now we have to check that 1 is related to which element here. Here we see that 1 is related to 1. It means that our 2 is related to 1 here, like the transitivity property, right? Next, come to the ordered pair element, 3 is related to 2. So now 3 is related to 2, and we see that here 2 is related to which element? 2 is related to 1. So now we can say that 3 is related to 1. Next, 4 is related to 3, and 3 is related to which? 3 is related to 2. So now 4 is related to 2. So this is the r square, means r composition r. So like that you can find out the r to the power any power of the relation. So now next is r to the power 3. You need to calculate r to the power 3. So r to the power 3, how can we calculate? R square composition r. Again you have to find the composition with r. So r square we already calculate. So now need to calculate the composition with r is this. So this is our r square, and the composition with, we have to take the r. So now what will be our r cube? Our r cube means r square composition r is this. So now how can we find this? First, again we see that our 1 is related to 1 here, and here we see that 1 is related to 1. So now our element is 1 is related to, ordered pair is 1 is related to 1. Next, come to the next ordered pair, 2 is related to 1, and we see here 1. 1 is related to which? 1 is related to 1. It means that our 2 is related to 1. Next, 3 is related to 1. So now 3 is related to 1. So 1 is related to 1. So comes is 3 is related to 1. Next, 4 is related to 2. So 2 is related to which element? 2 is related to 1 here. So it means that 4 is related to 1. So like that we can calculate it by the uh, composition. Clear? Next, we find here r to the power 4. So what will be the r to the power 4? How can we calculate this? This is r to the power 3 composition with r. This is r, the r ki power 3, it's already calculated, and this is our r. So now we find the composition. So now here we have r to the power 4. Same we do like that. First we check that 1 is related to 1, and we see that here 1 is related to 1 again. So now our in our 4 ordered pair is 1 is related to 1. Next, we see that 2 is related to 1, and we see that here 1 is related to 1. So here is 2 is related to 1. Next, 3 is related to 1, and we see that again 1 is here. So 1 is related to 1 again. So now our next ordered pair is 3 is related to 1. Next, we see here 4 is related to 1. Again, 1 is there. So 1 is related to 1. We see that. So now our next element is also 4 is related to 1. So like that, we can calculate any power of the R by the composition, right? Now, you see that here we have the r to the power 3 elements and the r to the power 4 ordered pair elements are same. So you can see that if after that suppose you calculate r to the power 5, r to the power 6, so they will be all are same. If one time you get the same ordered pair elements in r to the power, so that means that next powers of the r will be the given the same values. So here we see that r to the power n is equal to always now next values are r to the power 3, like r to the power 3 is equal to r to the power 4, means n equal to 4, 5, 6, you will get the same value, that is r to the power 3. So you can stop here and if you means you ask the question that calculate r to the power 5, 6, so you need not to calculate this, because if you have the same any power of the same ordered pair elements, then after further powers are also get the same ordered pair elements. Clear? Now clear how to calculate the composition. So now next is the counting relations. Counting relation, what is that? How many different reflexive relations can be defined on a set A containing n elements? Means if we have a set A in which we have the n elements, then how can you measure that how many reflexive relation will be there? So now we see that relation r, or how can we define the set? The relation is always the subset of a cross a, because here we have the only a set. If b set was there, so that will be a cross b. So now a set is only there, so our r is a subset of a cross a, right? And how many elements? How many elements? N elements in a set and another a elements in the n set. So total elements are n square, right? And square elements, because the multiplication of the elements, that is the elements in the relation, and square elements are there, right? So now therefore different relations on a can be generated by choosing different subsets out of these n square elements. So there are to the power n square relations. Means if you have to ask that how many binary relations should be there in a set. So how many binary relation? Total binary relations, that are to the power n square, if only talk about the a set. If we talk about the two sets a and b, so suppose a n elements in a set and m elements in b set, so what will be the elements? M n elements, and the total binary relations to the power mn. So here we have only one set, so we see that here the total element relations, how many relations you can form? We can form the to the power n square relations from these sets if we have the n elements in this set. Clear? So now come to the reflexive. A reflexive relation, we know that that must contain the n elements and ordered pair a for every a belongs to a. So we can choose only among n square minus n, right? N minus 1 elements to generate reflexive relations, right? So that our to the power n minus 1 of them are the reflexive relation. So if you can ask that how many reflexive relations are be there if you have the set a and elements n, then that are reflexive relations are to the power n minus 1. So you have to remember these relations. You have to remember like a formula, how many binary relations you have in the set to the power n square, how many reflexive relations are there to the power n minus 1 if we talk about the only a set. Similarly, number of symmetric relations, that value is to the power n plus 1 by 2. So you need to remember these points. How many total binary relations will be there? To the power n square. how many reflexive relation will be there? To the power n minus 1. And how many symmetric relations are there? To the power n plus 1 by 2. So now let's see which type of questions will be there. Let A, we have a set A in which we have the 10 distinct elements. So now the first question is that number of distinct binary relations on A. We have to calculate here, compute here that the how many distinct binary relations on A. And second, you need to calculate reflexive, how many reflexive relations are there on set A, and how many symmetric relations on set A here. So let's start here. We know that how many, here we see that n is equal to 10 here, number of elements in set is 10. So now, how many distinct binary relations in set A? We know that to the power n square. So now n is 10 here. So we calculate that to the power 10 square to the power 100. So to the power 100 binary relations are there if we have the 10 elements in the set. We can form to the power 100 relations, right? Next, we had compute reflexive relations. So reflexive relations are there to the power n minus 1. We know this. So now put here then equal to 10, then we get to the power 90. So reflexive relations can be formed to the power 90 here. Next, symmetric relations. So symmetric relations are to the power n plus 1 by 2. So when we put here n equal to 10, then we get to the power 55. So to the power 55 are the symmetric relations there if we have the A set in which the 10 elements are there. Clear? How can we calculate? So you have to remember these like a formula, that the total number of binary relations are there if you have the n elements in the set A to the power n square. Reflexive relations are to the power n minus 1. Symmetric relations are there to the power n plus 1 by 2. Clear? How can we compute this? Okay, so now today's lecture is completed now. Thank you. Be happy.